This is session number 10, peak fitting advanced. We're looking right now at a pure sample of indium oxide. It is conductive, it needs no charge referencing. So as we look at this data, we have to decide whether or not there's one species there, or two species, or three species. It looks fairly symmetrical at this point. Let's go ahead and do a little peak fitting. We should be able to use the peak area ratio. This is a 3D species signal, so it's a 6:4 ratio, or if you reduce it, it's a 3:2 ratio, or a 1.5:1 ratio for the peak area ratio. That's the theoretical peak area ratios. So let's draw a baseline like this. Surely, it's a little bit above. You can correct for that if you need to, or you can go back. Let's undo that, and instead use a linear baseline. Linear baseline is a little better fit. This has to do with the elastic scattering, and it does not affect our results that much. So we're going to go ahead and try just individual peaks for these two peaks. Add that peak. We drag the peak generator over here, add that peak, and we hit iterate the peaks. The reduced chi-squared comes out quite large, and if you look in here at the shapes, it's not necessarily such a good fit. Let's zoom in a little bit more by using the mouse. Okay, let's get this out of the way. Okay, perhaps we have not fully optimized the full width F max. Let's go ahead and try that. Let's make this a little smaller. We'll go down to 1.2 for that. And we'll drop this down to 1.2. We're just testing. We're not going to fix them. And we're going to hit start. And hit start again. More iterations. There's no real change. It's a poor fit here, a poor fit here, and a poor fit here. We could go ahead and do the peak area ratio, but that's not going to improve things. What this information means is that there is another chemical state, another peak, hiding underneath this peak envelope. So the peak max is to the left, so most likely the peak max needs to be over here where the true experimental peak max is, and we need probably to add another peak here. Okay, so what we're going to do, we're just going to delete all the available peaks, delete all, and start from scratch in a sense. So we're going to draw one peak here, and we're going to say add that. Another peak is there, we're going to add that, and we'll come over here, do the same thing, add a peak here, add a peak there. Now we're going to let it do its iteration. It has iterated. The results are a little bit better than before, 24. This large number is most likely due to this inverted baseline aspect here. So we'll leave it alone for the moment. But if you look at this, we have a better fit. It's not an optimized fit. What you might want to do is to go in and make the peaks a little broader and see if what they optimize out to be. Put a 2 there, put a 2 here. We're adjusting the full width F maximum to be wider, and then we're going to iterate again. Start to fit. Okay. Now the chi-squared has dropped a little bit. It's down to 13. Fit looks a little bit better. If we play around a little more, we can improve this even more. The peak widths are in the range of expectation, 1 to 1.5. If you were to go study the literature, you'd find that this is the indium oxide peak, and this is due to indium trihydroxide. Question is, what is the optimum ratio of these two? We can start to sort that out by applying a ratio here. We can do a constraint. We can A and C are related to each other. This large peak here, A, this large peak C. It's a 1.5 ratio. So we come down here. We want to link A with C. It currently says 1.26 for the area ratio. We're going to make it 1.5. Now we'll come up here and do the same thing with B. We're going to link B with D. And it's too large. We're going to make it 1.5. We're going to make it the theoretical ratio. Now we have to tell it to iterate again. Okay. We're using theoretical information to try to improve our results. It has shrunken a little bit. The fit up here is a little better. Fit down here is good. The fit down here is a little bit off, but unless you're really needing to go into the theoretical nature of the chemical, this is a sufficient result. If we wanted, we could go in and change the labels, as we've told you before. There's a chance to fix all binding energies or the full width F maxima. This is useful for the first iteration. It's not necessarily useful for all time. Here we can generate atom percents from the survey spectra. Currently we have carbon, chlorine, indium, and oxygen available, so whichever one you display is corresponding to the data from the survey spectra. If we were to use this, we would be building a peak table, summary peak table. We're not going to use that at this moment. You can open up the default parameters and change them. Currently 80% Gaussian, no asymmetry. We can control the binding energy position, the full width F max, the height, the ratios, and we can control the amount of iteration, the divergence in each iteration. Okay, so 0.1, here it goes on a percentage basis. You could actually print the table if you wanted. This is pretty much the advanced peak fitting course. Thank you.